One of the good things about this coordinate, which is going to be quite useful, is it completely separates the acceleration in the normal direction and tangential direction. Acceleration in the normal direction is a function of speed all the time. It doesn't have anything to do with change in the speed. But we usually think acceleration is change in the speed, which is not correct. It is change in the velocity. So if the speed is even constant, or even if it's changing, it doesn't really matter. Acceleration in the normal direction is going to be a function of velocity, or a function of the speed and the radius of curvature. But in the other side, acceleration in the tangential direction is change in the velocity. It is dv dt, not as a vector, not as speed, not as velocity, but speed, derivative of the velocity with respect to time. And it has a positive point in it, which comes from this equation. Look at this. Acceleration in the tangential direction is dv dt, right? Which is quite similar to what we had for acceleration on a particle which was moving on a line. In that problem which we worked on it a couple of videos ago, acceleration was dv dt, right? But here acceleration in the tangential direction is dv dt. And all the equations that we learned over there is going to be again valid for this one. The only thing you need to do is you need to replace the accelerations that you had in that case on the linear movement with at, or dv dt, right? For example, if or what's the meaning of this? If you have a complicated path of movement, anything, let's say this is the path of movement of this particle. So this particle is moving here. All the time we have this equation for it. At is equal to dv dt. And also velocity or speed means change in the length or displacement divided by time, right? So if I show the location of this particle with a variable like s from a point like O, the origin of this coordinate. If I show it with s, so s is the length of the path from the origin to the location of P. Then speed, v is gonna be ds dt. Exactly like what we had for movement of a particle on a straight line, right? We had the same equations for that. And even we can derive the third equation, the time-independent equation. If you divide these two equations together, dt is going to cancel out, and we are going to have at times ds is equal to v times dv. And also, if we have constant at, or v dot is constant, then we can integrate these two equations, these three equations, and find the algebraic equations we had for movement on the line. Exactly the same equations. The only difference is acceleration in those equations is going to be replaced with at. So if v dot is constant, and if I integrate this, again, I'm going to discover or recover these equations. Velocity, or speed, more accurately, is going to be the initial velocity plus at times t, or v dot times t, right? And position is going to be initial position plus initial velocity times t plus 1/2 of at, or we can write it v dot times t squared. And the time-independent equation is going to be velocity squared minus initial velocity squared is going to be equal to 2 times at times s minus s naught. What is the meaning of this? It means you can assume this path, this curvy path, just stretch it and make it a straight line. It's going to look like just a movement on a straight line. This is your origin, this is the location of P, and the distance from O to P is S. And all the equations that we have here is going to be valid for this curvy movement. The only thing we don't have here, which is belong to this movement, which we don't have it here, is the acceleration of this particle in the normal direction, which is a function of velocity, right? So we don't have that acceleration in any of these equations. So whenever we have a curve movement and let's say v dot or change in the speed is constant, then we can assume this path, this curvy path is just a straight line and have all of these simple equations for this complicated movement, which I'm going to use this to solve some problems.